we are going to introduce a very important property of frequent patterns, which is called the downward closure property of frequent patterns. Let's look at this simple transaction database, TDB1. It contains only two transactions, T sub 1 and T sub 2. Suppose we get a frequent item sets A1 to A50. Then we actually can clearly see all its subsets, like A1, A2, or A1, A2 as an item set. They are all frequent. Okay. Then you may wonder, there must be some interesting hidden relationships among different frequent item sets. Actually, there's one called downward closure property of frequent patterns, which is also called the Apriori property. Okay. Now let's look at this. Suppose we know beer, diaper, nuts. This item set is frequent. Obviously, beer and diaper should be frequent as well, because any transaction which contains beer, diaper, and nuts must also contain beer and diaper as an item set. That's why the beer, diaper as an item set should be at least as frequent as beer, diaper, and nuts. So we can easily derive this property so that any subsets of a frequent item set must be frequent if we keep the minimum support threshold as the same. So in that context, we can derive an efficient mining methodology. The general philosophy is this. If you find an item set S, any of its subset is infrequent, then there's no chance for S to become frequent, because based on this Apriori property, then we do not even have to consider to mine S. This actually turns out to be a sharp knife for pruning. So this a priori pruning, based on this, it generates quite a lot of scalable pattern mining methods. So the first a priori pruning principle was discovered by Rakesh Agarwal and Srikant in VRDB 1994. Heike Manila in KDD 94 workshop also generated a similar methodology. The methodology generally says if there's any subset, any item set which is infrequent, then its superset should not even be considered or not even being generated. Okay. Based on this, there are three major approaches developed in subsequent studies. One essentially is Apriori. The first representative work was published in VRDB 1994 called level-wise join-based approach. Another method was developed by Zaki et al., and what they got called ECLAT is based on vertical data format. Then the third approach essentially is pattern-based. It's frequent pattern projection and growth. It's pattern growth approach called FPGrowth, developed by us in year 2000. Hi, let's introduce the very famous Apriori algorithm. This algorithm is the first candidate generation and test approach for frequent pattern mining. It is a level-wise candidate generation and test approach. Initially, the first time, you just scan the database once to get frequent one item set. Then taking this frequent one item sets, you are going to generate length 2 candidate item sets. At the case iteration, you are going to take length k frequent item sets to generate length k plus 1 candidate item set. Then you go against the database to test these candidates generated and to find the real frequent k plus 1 item sets. Okay. Every iteration you set k to k plus 1, so you can go until no frequent item sets will be generated or no candidate item sets can be generated. Okay. Then after you exit from loop, you just return all the frequent item sets derived. That's the algorithm. Let's look at the pseudocode. We set C sub k to be the candidate item set of size k, F sub k to be the frequent item set of size k. Initially, we just get frequent one item sets. Okay. Then we get into the loop. Suppose the frequent k item set is not empty, then we get in, we use k's frequent item set to generate k plus 1's candidate item sets. Then we go against the database using the minimum support to see which k plus 1 candidate items are all frequent. Okay. We derive the frequent k plus 1 item sets. Okay. Then we reset k to k plus 1. Until we get out of this loop, we just return all the frequent k item sets for all the k's derived. Okay. Let's look at the concrete example. Okay. You look at this transaction database. It contains only 4 transactions. Okay. The first scan, you just try to find their support for every single item set. Okay. Then we find D, the support is only 1, so it's not frequent. So then we just remove it. We get a frequent 1 item sets and their support. Okay. Then we use this to derive the candidate 2 item sets, C sub 2. Then we scan the database again. We find their real support count. Then we find these 2 blue marked ones are infrequent. We derive frequent 2 item sets. Then using frequent 2 item sets, we derive the frequent 3 candidate item sets. Remember, this one you probably can see a big cut. Why? Because you probably see A, C, B, C are frequent. You may think A, B, C could be candidate item set. But A, B is not frequent here. So A, B, C will not be derived. So we only derive B, C, E. Okay. With another scan, we find its support is 2, so it's frequent as well. Then we find all the frequent 1, 2, 3 item sets. The concrete implementation actually involves self-joining and pruning. Self-joining goes like this. Okay. We get ABC, ABD. The first 2 are the same. The third one is different, so we generate this self-join, generate this candidate set. Okay. A similar thing, we get ACD, ACE. The first 2 are just the same. The third one, we get them together, we get this candidate sets. But, okay, we may need a pruning process. The pruning is pretty simple. Before you count against the database, you probably see for ABCD, this BCD is there, so this is a candidate one. But for ACDE, CDE is not in the frequent 3 item set, so ACD cannot be the candidate, so it's pruned. So that's the simple way you can see self-joining and pruning, we can solve this problem. Okay. So finally, we get only 1 candidate sets, A, B, C, D. Let's look at the SQL implementation of this candidate set generation and test. So we probably see the candidate generation essentially this. Okay. You probably see the self-joining, how to do self-joining. You will see the first k minus 2, they are all identical. Then the last one, k minus 1 item, one is smaller than the other, we get 1 candidate set. Then for this candidate set, we still need pruning. The pruning essentially is to check whether these subsets, the k minus 1 subset, containing this one. If S is not in Fk minus 1, then we just delete this candidate from the candidate set C sub k. So this is the candidate generation, the key step of SQL implementation of Apriori. Since the proposal of the famous Apriori algorithm, there have been many interesting extensions or improvements towards this method. Let's just examine some of them. Okay. So the first line of work is how to reduce the number of passes of transaction database scans. We know the database scan involves disk accessing, which could be quite expensive. But if you want to find size 10 frequent item sets, likely you have to scan this database 10 times. That's quite expensive. To reduce the number of scans, so there are several publications. One is called partitioning method, we're going to introduce. Another one called dynamic item set counting method. You'll probably notice the first author, Serge Brand, who was a PhD student of Stanford University. The second year, 1998, he actually proposed one of the most famous algorithms, PageRank, and set up a Google company. Okay. So another line of the work is how to shrink the number of candidates. You generate a very large number of candidate sets in many cases. How to shrink the number of candidate sets to be generated could be a big saving. Hashing method is an interesting one. For mining max patterns, Bayardo also proposed pruning by support lower bounding. Another interesting method is Bonin proposed sampling method. The third line's work is to explore some special data structures, like some tree projection method using H-tree to do H-minor. And hypercube decomposition is another interesting method. We're going to introduce a new tree structure called FPGrowth. Let's look at the first one, partitioning method. Partitioning method guarantee you only need to scan data twice, before you generate all the frequent item sets, no matter for how many Ks it is. So they observed a very interesting property called any item set potentially frequent in the transaction database must be frequent in at least one of its partitions. That means, suppose you get a global big database, big transaction database, you partition them into K partitions. If an item set X is not frequent in any one of these K partitions, it cannot be frequent in this global transaction database. Why? You probably can see. If you got an item set X, which is not frequent in the first one, not frequent in the second one, not frequent in the case one. So you add them together. You add all these support together, you get a global support. You add all these database together, you get a global database. You probably can see if everyone is smaller than sigma times its size, then finally the global one were also smaller than sigma times the size of global database. That's why at least one of these database contain must be frequent. Okay. So with this observation, okay, you can see this partitioning method will need only 2 scans. The first scan is you partition the database into K partition database. How do you partition them? Each partition you want them to fit into the main memory. Why? Because no matter how you scan them, you will not involve any database IOs. So that's the reason you can scan once you put them in the database, you can work on it to derive K frequent item sets for no matter how many Ks you can get. Okay, that means you can derive all the local frequent item sets. Okay, then based on this property, you can do the second scan like this. Okay, you can say, since any frequent item set in one of these K transactions can be potentially frequent, so the globally candidate sets which is frequent in any one of them, it will be a global candidate item set. Then the second scan, you just count against each database, count those counts of the global candidate sets. Okay, then you will get their count, you add them together, you will be able to derive global frequent patterns. That's why this method guaranteed to scan database only twice. So this is pretty interesting. Another method I'm going to introduce you called directly hashing and pruning. This method is trying to reduce the number of candidate sets based on hashing and pruning techniques. The general philosophy can be like this. Okay. The observation is, if the k item set is frequent, then in this hashing bucket, it contains several potential item sets. It must be frequent. So if the hash count is not frequent, then any one of them cannot be frequent. The general philosophy like this. Okay. While you are going to derive the frequent one item set, in the meantime, you set up a hash entry for the potential two item sets, but why you set a hash entry rather than count each one? Because there could be many, many distinct items. So the frequent two item sets before you get a frequent one, the candidate two could be really, really big. But if you set a hash entry to get several items share one hash entry, the whole hash table will not be too big. Okay. Then the interesting thing is, while you derive frequent one item set, you also can cut many two item sets. They cannot be frequent. For example, suppose our minimum support count is 70. Then this one has only 35. This one has only 58. That implies those items, none of those items can be frequent because they share this entry. Their support count is still below the threshold. So only the second one, this BD, the support is quite big. Past the support threshold, this may contain the real candidate sets. Okay, that's the reason you can reduce the number of candidates substantially using this hashing and pruning method. Now we are going to look at another interesting pattern mining method. Is mining frequent patterns by exploring vertical data format. This method is called ECLAT, or equivalent class transformation method. The general philosophy looks like this. Okay. In original transaction database is horizontal data format. In the sense, you get every row, you get transaction IDs and a set of items in this item set entry. Then you can transform this horizontal data format into vertical data format like this. For every item A, you will see which transaction IDs associated with this item A. That means A bought in which transactions. What's the benefit of this? The first thing is you transform the item set into TID list. The total size is approximately the same if every entry or every ID, they have the similar number of bytes. But the way to compute this will be different. With this TID list, for example, if you say, what is TID list of E? You get 10, 20, and 30. What is TID list of A? You get 10 and 20. Then how to derive AE? You just intersect them together. You can see you intersect this set with this set, intersect two TID list. You derive the TID list of these AE, this item set. If this one contains sufficient number of transactions, that means it's frequent, like 2, then AE will be frequent. If this one is infrequent, then you don't need AE to go further. That's a similar thing as Apriori principle. Then the properties of TID list basically say, if this two TID list is equivalent, that means they have the same set of transactions. If this one is a subset of the other one, that simply says the transaction containing X must always containing Y because this one is this one's subset. So you probably can see if we try to derive frequent patterns based on this vertical intersection, we just need to see the size of these transaction list. But there's one interesting method called diff set to accelerate the mining. The reason is when you get a very large number of transactions, each item may be associated with a very long TID list. Then their intersection, like this E and the CE, their intersection could be small, but their difference could be small. So you look at the intersection is large, the difference could be small. For example, you intersect these two. The intersection is 10 and 20, but the difference is only 1. So you only keep this. You don't have to keep TCE. That may save a lot of space. Okay. This is the general idea. Using diff set, you can further improve its efficiency. Hi, I'm going to introduce you another interesting pattern mining approach called pattern growth approach. This approach is represented by an interesting algorithm called Apriori. Let's look at how this algorithm works. The general idea is first we mine the frequent single items, and then we partition the database based on each such item. Then we recursively grow frequent patterns by doing the above iteratively or recursively for each partition database, also called conditional database. To facilitate efficient processing, we use a new data structure called FPGrowth. The whole mining can be summarized as follows. We recursively construct and mine conditional FPGrowths until the result FPGrowth is empty or until it contains only one path. This single path will generate all the combinations of its subpaths, each of which is a frequent pattern. Let's look at a simple example. For this transaction database, it has only 5 transactions. Each contains a set of items. So we can scan the database once, find the single item frequent pattern like the following. Suppose minimum support is 3. We will be able to find the following frequent single items. Then we can sort the frequent items based on its support frequency in descending order like this. Based on this, we can construct a tree by first construct a header following this order, then scan the database. We can construct this tree as follows. For example, okay, if you look at the first transaction is FCAMP, so we construct FCAMP with only support as 1. Then we get FCABM, we constructed this FCABM, and this part support becomes 2, this maintains to be 1. Then we can go this one, one by one, we will construct the following tree. Then to mine this tree, we can use divide and conquer and do it recursively. We can do it like this, okay. For each such tree, we can construct this pattern base. We call P's conditional pattern base, M's conditional pattern base. Let's look at how P's conditional pattern base is constructed, okay. So you probably can see P is the leaf of the node. You only look up, you get FCAM. The support is 2 because P occurs together with this branch only twice. That's why you get FCAM2. Then for the same reason, you look at the other P, its CB happens only once together with P. That's why you get CB1. Okay. Then if you want to look at the M's conditional database, the philosophy, you were thinking the patterns having M but not having P because P already been taken care of by the P's conditional pattern base. So you look at the M's conditional database, actually you also look up, you get FCA. So for this branch, it occurred twice. That's why you get FCA2. For the same reason, you look at this M, you get FCAB1. So you get FCAB1. You can do this on and on. Then with this, you can, get it into transform the prefix path of P, you get the following. Okay. Then the remaining task is just mine this conditional pattern base. For this conditional pattern base, we mine single item patterns. We construct this FP tree and mine it recursively. For example, for P's conditional pattern base, you will get only C3. The reason is F, A, M, and B, they never occur more than 3 times, so they are out. They are not frequent, you only get 3. But for M's conditional pattern base, you can see FCA really occurs 3 times. The B only occur once, then you get a FCA3. And B's conditional pattern base, you probably can see none of them actually pass the support threshold of 3, so it's empty. So let's just look at, of course, you will get A and C's pattern base like F's3 and FC3. Actually, for this single branch, you can dump all the possible combinations there support all 3. But we just look at in the recursive way how we can mine this pattern base. For this pattern base, you probably can see, you can say for A's conditional pattern base, you'll get this, you get FC3. And for C, you get F3. You can see that's the same thing. Then for this particular AM conditional FP tree, you just take a C, you say C's, that means AMC or CAM. Their conditional pattern base is only F3, you get this. Then you can dump all the patterns, like this. For single branch, essentially that's the same thing. You will dump all the patterns, like all the possible combinations, they are all 3. You probably can see if you get a single prefix pass, you actually can partition this into 2 parts. Like this pass, you can mine it, and this part you can mine it, then you can just concatenate the pattern results. What about this tree cannot fit in the main memory? If it cannot fit in the memory, we can use database projection. That means we project the database based on the patterns, based on single item set. Okay, so then we can construct and mine this tree for each project database. So we can have parallel projection or partition projection, 2 different methods. The parallel projection means for this one, you will get a F4 project database and F3 project database. For example, for this first string, you will see GH, suppose it's not frequent, only F's are frequent. You will get a F4's project database, you get a F2, F3. Okay. Then F3's projected database, you get F2. That's the one. Then every one of these projected databases is independent of the others, so you can mine them in parallel. But then you also can have partition projection. Partition projection, the general philosophy is for each string, you only put into one place. For example, this one contains F4, you only put F2, F3, but you don't put this F2 to F3 projected database. When you finish mine this F4, when you do this projection, then you think this one is related to F3, you will put this one into F3. Okay, so that's just different choices, for different partition or parallel projection. It's just different way of implement it. Thank you. Hi, in this final session of this lecture, we're going to discuss mining closed pattern. As we already know before, closed pattern is a compressed form, but it's a lossless compression of frequent patterns. So mining this closed item sets is very interesting and useful. Okay. And with pattern growth approach, there's one interesting method developed called Closet Plus. Let's look at this Closet Plus, how to develop efficient direct mining of closed item sets. So let's look at this transaction database. It contains only 4 transactions, and these are the items in these transactions. Suppose the minimum support is 2, we'll be able to get these as frequent item sets, and based on this, we can work out the F list like the following. Okay. Now we look at an interesting method developed called item set merging. Okay. The philosophy can be represented using this example. Okay. Let's look at these projected database. Okay. For these projected database, we will have ACF, EF, and ACF based on this. You can see these project database will get ACEF and ACF. But the interesting thing is ACF happens in every transaction projected in this database. ACF have the same support as D. In that case, we can grab ACF out from ACFD project database, which contains only one item E. It is not frequent. Therefore, we will be able to get ACFD support is 2. It's the final result. This method called item set merging simply says if Y appears in every occurrence of X, then item set Y is merged with X. Now the X is D and Y is ACF. ACF occurs in every occurrence of X, which is D. Then we will merge ACFD together to form a more compressed form. That means you can mine all these immediately. Okay, so this is more efficient. Actually, there are many tricks developed in CLAT+. For example, hybrid tree projection. We use bottom-up physical tree projection and top-down pseudo tree projection. There's one technique called sub-item set pruning, item set skipping, efficient subset testing. But I'm not going to get into the details. For details, you can read this paper. Okay. So finally, I'll summarize the recommended readings. These are all classical papers on, Apriori, Apriori mining, and the further improvement of Apriori mining. Then we have vertical methods, we have FPGrowth methods, and we have CLAT+ methods. So finally, there's an interesting survey article called Frequent Pattern Mining Algorithms, which contain many more algorithms covered in this lecture. If you're interested in, go ahead and read this chapter.